Hello, my name is Ethan Rashad, and I currently work in the Wertheim Building of Engineering underneath the instruction of Dr. Angelini. My research focuses on the presence of peristalsis in 3D printed epithelial tubules. To give you a quick introduction on what 3D bioprinting is, it's essentially normal 3D printing, but instead of using a plastic material, we actually load a syringe with live cells, and then we can extrude those into a gel medium. Once those cells are extruded into this gel medium, we can then manipulate how we want to place these cells, creating fine structures smaller than the cellular level. In this picture here, we see a 3D bioprinted knot. This just shows you the different types of complexity of curvatures that we can create. You might know 3D bioprinting because something revolutionary can happen. We could 3D print organs. In the US alone, there are over 100,000 people waiting on the transplant list. And transplant surgeries typically cost you $300,000. Now, if we were to use 3D bioprinting, we can actually reduce those costs to only $10,000, making it more accessible to many patients, saving more lives. In this figure here, a mandible and an ear were created, and those were shown to have viability rates of 92%. The only limitation with printing out these organs is that these structures aren't very vascular, meaning they don't require a lot of oxygen and nutrients to keep them alive. In order for the future, if we want to create more vascular structures, we have to understand a deeper level of vascularization. The cells that we're going to be using are called MDCK cells. What's special about these MDCK cells is they don't just divide normally and go all over the place. When they divide, they actually like to form these hollowed out rings called acini. Now, our hypothesis is that once we have these cells and they go adjacent to each other, they'll then connect and form these long epithelial tubules. And this is where peristalsis comes into play. Peristalsis is the involuntary constrictions that happens in your digestive tract. This helps propel different fluids and helps absorb nutrients. Understanding and observing if peristalsis occurs in these 3D printed epithelial tubules can help impact our understanding of vascularization. So how do we do this? The first thing we have to do is create 5 linear equations. And once we have those 5 linear equations, we can then rearrange them to create a nice rhombus shape. We do that using MATLAB code. And once we have that MATLAB code, we then translate that into something we call G-code. Once we have G-code, that's essentially our 3D printer's language of how it can function. To gather our cells, we have to passage our cells, and at the end of that, we'll have a cell pellet. Once we have this cell pellet, we can just insert our syringe and suck up all the cells. Once we have our loaded syringe, we just attach it to our printer, and then we hit the print button. Over here in image A, it shows our expected MATLAB predicted rhombus shape. What we're looking for is a nice bisecting line and very sharp vertices. Using a 100 microliter syringe with the corresponding flow rate and translation speed, we're able to create our first rhombus structure. However, this was not perfect. We see there's a lot of inconsistencies and our bisecting line isn't fully touching. However, when we switched to a 25 microliter syringe, it was a lot more consistent and the lines were a lot solid, which is good. However, our bisecting line is still a little bit crooked, but it still showed improvements. A good analogy to understand this is frosting. If you want to add frosting to a cake, you have your frosting pipette, and let's say if I squeeze really hard and I just moved it really fast, you wouldn't have as detailed structures and designs on your cake. But if you had your pipette and you squeezed it just very precisely and moved it slowly enough, then you can create much more detailed designs, which is essentially what happened in figure C. This image here shows what was once a rhombus but got split into fragments. We believe this fragmentation was caused through our actin and nucleus staining, and with that, bubbles formed on the side of our wells, and when these bubbles expanded and they ruptured, it caused fragmentation of our rhombus design. Although this happened, this did not stop us from being able to image. Day 3 shows essentially no evidence of tubular formation, it's just a glob. However, once we get to day 7, we do see this U shape starting to form, which shows that we have evidence of our tubular formation. Day 10, we see something similar. This time, the cells become more dense and compact with each other. A good observation that we can figure out from this is, and once we measured the tubule length, we found out that image B here had the greatest diameter, which means that once it's printed, the cells have to proliferate and create more. And once they have enough cells, they can say, okay, now let's create our tubules. When we wanted to study peristalsis, we were limited on the amount of time. So the cells imaged for our time lapse were only day 2. And as seen in the last slide, there was no formation on day 3. So it's hard to study peristalsis in these tubules when they're very premature. When we play the time lapse, we just see bleaching of the cells, which is like flashing because the fluorescent molecules start to break, but we don't see any big wave-like motions. However, this does not limit us. We can do further research on matured tubules, and then we can help figure out if peristalsis really does exist. We hope that the future studyings of this can help pioneer research to create a better understanding of vascularization. Thank you. My references. Are there any questions?